I got it.
Being live streamed. Okay. Okay, welcome everybody to the February 13th general meeting of the Los Angeles Astronomical Society.
Yeah.
Remember that we are being live streamed and recorded. Are there any new members that would like to say hello and introduce themselves tonight? No new members made it to the meeting? New members dropping in?
I'm a new member. I'm David Thomas.
Hey, David, how are you?
Fine, thank you.
How did you find us, and tell us a little bit about you?
Well, I work part-time as a museum guide at the Griffith Observatory.
Huh.
So I've known about your group for quite a while, but I've been a member up where I live in Ridgecrest. So I've been a member at the China Lake Astronomical Society for a while. And I guess now I'm a dual member.
Mm-hmm.
So I decided to join this group as well because I might want to actually join some of the public star parties at the Griffith Observatory.
Good.
Fantastic. Welcome, Dave.
We'll love to have you.
Hope to see you there.
Good.
Thanks for joining us.
We also need outreach members.
It's a little far.
If you see from work, we might go from the observatory. Okay, I have some upcoming events. We have a dark sky night at Lockwood on the 18th. But be aware that 10-day forecast has the high for the day at 46.
Let me guess, low is going to have a minus sign in front.
No, it's a 35 low, but it's been really cold at Lockwood. So if you're thinking about going, go to the website and go to the Lockwood part of the website and look at we have live cams. Look at the weather. There's a weather station there.
The camera is broken right now.
Right.
Camera's broken. Weather station.
Well, the all sky cam is working, but the one that's pointing south is broken, and I haven't been able to get up there to fix it. So.
Weather station up.
The weather station itself is reporting the temperature and all that stuff.
Okay.
But the video feed is stuck as of a week ago, 2 weeks ago.
Okay.
When's the next star party at Griffith?
Say again.
When's the next star party at Griffith?
The next star party at Griffith is on the 18th. No, it's on the
25th.
25th.
I have it right here.
2 weeks. 2 weeks on a Saturday night.
2 weeks it is.
Okay.
Always Saturday night, once a month, Any usually. new members?
And I heard we could no longer drive through the park. That's closed off for bicyclists.
What?
What?
That makes no
Where'd you hear
sense.
that?
No, I saw bicyclists last star party.
I thought that they had a bicyclist that was killed, and I heard on the news they closed off one of those main sections.
They closed off some of the roads, but I think that the loop up to Griffith is still open. Yeah, but they have restricted some of the roads in Griffith Park to
I think some of the riding trails too. There's riding trails that they may have closed down.
As an employee at Griffith, there's no indication that we're closing down. If they close down that road, we have to close down. There's no indication we're closing down.
No.
So it's not that road.
Well, I'm coming from the valley. If anybody can get a map of how I can go through Griffith, I'd
The
love
only
to see
way
it.
you can do that, you got to approach it from the south, either Ferndale from the west or Vermont or Hillhurst from
Vermont.
the east. That's the only three roads, and you can't approach it from the north. You got to approach it from the south. Okay.
They all lead
Google
to
it.
the same place. And if you're going to go up for the star party, make sure that you get in on the email for the parking pass.
Yeah.
For the
Otherwise, you're
parking
not
lot
going to
up
be
there.
able. You're not going to be able to attend.
Yeah.
And I would
Because
like-
well, you can attend, but if you're going to park anywhere near there, I was astonished last time when I parked. I was waiting. I think I was waiting for Tim to show up for us to do the tent, and I looked up and it said that the parking was $10 an hour, an hour.
Yes,
I was
that's absolutely true.
So be ready for that. If you actually need to park there, don't have a heart attack because you already know.
You would park at the Greek Theater and take the shuttle.
Greek theater.
No,
and
but then you
shuttle.
can't take your equipment.
Yeah, that's tough.
What are you gonna do, Zoli?
And while I want to make sure
You leave
everybody
it home.
that the Griffith is well attended on those nights is because I'm with a separate sidewalk astronomy group in Monrovia, which is always the same night, the first quarter moon on a Saturday. If for anybody who's living in the San Gabriel Valley, if you're looking for some places maybe a little closer, is we do sidewalk astronomy at the corner of Myrtle and Lime in Monrovia on that same night. But first choice would be the Los Angeles.
David, can you put that info in the chat for people to pick up?
Yeah, I'd be happy to. Yeah, I'll do that.
Okay, that'd be great.
Thank you, Daryl.
Sure, no problem.
Are always a.
I'm sorry, is there a question?
Who was that?
It's okay. Okay, the other thing is all of the people that are here, if you have a telescope or if you don't have a telescope, we really need more people in the outreach program. We're trying to cover a lot of requests with the same amount of people because we're not getting new people and they're getting tired. So new people, please get connected with the Night Sky Network. It shows what the outreaches are, and you can contact Evan and get on his list. Even if you're not, you can't go to every one. If there's one around you, you can jump on that one. And this is how we need to do that. We need a much bigger roster of people so that when Evan has one, he can pull the people and get enough people that are close by at any time. So tell everyone else that you know that's in the club, please think about taking your telescope or not. You could go without a telescope and just help out whoever's there too and talk to the people.
I live in Orange County, and most of them are up around Pasadena and places like that, which is a schlep. Do they have any kind of down south, a little bit at least in the LA area or not?
Yeah,
well, Evan puts out the list, and the outreaches are also on the Night Sky Network calendar. So you look and see the info on the calendar, and then you'll know whether it's near you. And then contact Evan and say, hey, this one's really close, I can be there. And that's all he needs to know. Then he knows how many people he's got coming, and he can cover. If we got enough people, we can cover more requests. We're getting pretty popular, and we're getting a lot of requests. I would like to be able to make all of them if we can.
If I may make a comment there, we need people in the San Gabriel Valley because already a friend of mine who is a coworker at Griffith was turned down by us because, and I talked to Evan about this, he claims I'm the only one in the San Gabriel Valley. Now, I find that very hard to believe considering how many people show up over at Garvey Ranch, which is definitely in the San Gabriel Valley, but that's what Evan claimed. Now, so anybody in the San Gabriel Valley, really think about attending some outreach because apparently we're thin in that region. And I think 3 or 4 of the following outreach events in February and March are pretty much in the San Gabriel Valley. That's where we're thin. San Fernando, we got tons of people, apparently.
Hey, David, also, please reach out to the Old Town Sidewalk Astronomers because the San Gabriel Valley is what we do. And we got a lot of folks there that, contact us.
I am not the contact point.
Oh, okay.
Evan.
Well, I'm sorry. So whoever is, if you need support in the San Gabriel Valley, just try to give us a heads up. I mean, again, we've been doing it since 2004. We're doing our own thing, which is cool. And so, but we're very happy to help out as long as it's kind of what we consider local. So
now Evan
we can help support that.
Evan has posted the February and March outreach events in the group IO. I suggest that you contact him directly.
Well,
I'm not going to act as an in-between.
Yeah, and we supported the Sierra Madre school event. There's another one that was posted that we're also supporting.
Yeah, but Sarah.
Okay, guys. We get the point. We get the point.
No. But Dave,
we get the point. He knows who to contact. Contact Evan if you need some help.
Yeah.
He'll contact you. Just get together with Evan, exchange emails so that you can contact each other if you need each other. It's pretty easy.
I'm gonna drop few links for you guys in a few minutes.
I'm sorry, say again, Joel?
What was
I'm
that?
going to drop few links for you guys for the outreachers. So
Okay, great.
let's keep going.
Okay, let's see. What else have I got to explain?
Daryl, I have one question about parking.
Yes,
Last time when I went up there, I know the parking was really tight. I mean, the crowd was huge. Now, we went around and went up to the beginning of where you make that left turn and you go into the lot for us. Well, that part was just stopped. You just couldn't, you had to wait for everyone that didn't have a parking pass to park. While that gate was like closed, you had to make a big loop. And finally you got into the area, it was totally open for us, you know.
I understand what you're saying, and that's something that we might be able to talk to them about, and putting the entrance to our part in a different place. I saw what you were talking about, because people were waiting for someone to back out of a parking place, and then they'd pull in, and somebody else would back out. I saw everyone waiting. So
I think I stayed there about 10 minutes just waiting for that to open
yeah,
up.
I agree.
Since I work at Griffith, I could tell you right now, there's one entrance and one exit. You try and get in on the exit and you're going to create chaos.
David, that's not what we're talking. David, that's not what we're talking about. We're talking about an entrance to the parking area that's reserved for us.
Yes, I'm talking about that right now.
Okay.
Sometimes they
That's
use the old
the problem is, everybody shut up. Because I'm from Griffith and I know that area. The thing is, there's one entrance, and unfortunately, parking and road control leave something to be desired up there. I would highly recommend, because they tell the employees this, okay?
Can you make it short?
Yes. Get there early. Okay?
Agreed.
I was there about 2:30 or 3, and it was just about what I say.
Yeah.
Then sometimes, Dawn, it's a zoo, no matter what time of the day you get there.
Okay, guys, this is not what we need to talk about right now. Come on.
All right.
Let's
Fine.
move it along. I got
What
more
about what meeting?
information here. The other thing I have for everyone is, let's see. I'm going to drop in the notes all of the 60-inch nights and the dates. I'll drop in, where's the notes now?
Well, we can see them on your screen at night.
Okay, I'll still drop them in the chat so people can cut and paste them here. Okay, and contact me, get a spot. Okay, I think that's all I really have. So we can go on to Secretary's update.
Okay, so you want to advance the next slide? So there are two parts to this. One is just an announcement that we're revising the bylaws, and basically they need to be revised to reflect the fact that we're doing, well, the old bylaws assume that we're doing all in-person meetings and that the voting is done in person. So we're revising that and just correcting a few typos, things like that. I'm not going to go into a discussion of those changes. They're all posted in Groups.io under user guide. And so that's the link that is shown on the slide. And just go in there. And so the board will vote on the revisions at the April 5th meeting. So any comments, either post them in the discussion group on user guide or send me an email with the comments. Okay, next slide. And this is just a membership update. So we're, I just pulled the numbers last night and we're at 996 members right now. And we had 4 more apply just in the last 2 days. So those, that should, we're well, anyway, we're inching towards 1,000. We did switch to Wild Apricot for membership management just because the old manual process of managing spreadsheets was just getting too cumbersome and too error prone. So since October 2022, we've been accepting all new memberships through the Wild Apricot system. And last month, or actually in December, I started doing renewals through Wild Apricot. So those of you who get an email from Wild Apricot from LAS, that's not spam, that's legit. The three things you have to remember about Wild Apricot is that you have to register an account. And so your account is your username, your username is your email address. And rather than setting up default password for everybody, just use the forgot password to activate the account. You will have to log in to renew, change addresses, add or drop your Griffith Observer, change your membership level, so on. And something that the Wild Apricot just implemented just 2 weeks ago was that all passwords will expire yearly, and they have some complexity requirements that you'll see when you go to change it, or you can opt to use your Facebook account to log in. And I just want to call any questions about Wild Apricot? Okay.
What is it? I really didn't.
Wild Apricot is a commercial membership management package.
Okay.
So we have to, it's a subscription model. We pay a certain amount per month for that, but that's a lot easier than, automates a lot of the stuff that I was doing by hand. So I used to call all the email addresses of people whose renewals were due, send them out, and then process the renewals by hand. So those are all being done automatically by Wild Apricot now. And so it's made life a lot easier. I just wanted to highlight one thing on the membership. You see that we peaked around 800, right? That peak, the first peak is right. When we had the announced that we're going to be sponsoring or organizing a trip to see the 2017 eclipse, but you had to be a member. We got a big jump in membership, and then as the membership expired, that tapered off. And then with COVID, we started seeing a peak again. And I think, you can speculate as to what the cause of that, but I think the suspicion is that people bought telescopes and other things during the lockdown, and that generated a big interest in our club. So any questions about this?
Thank you everyone who does outreach, because it really shows to me right here, because the more members that we get, the enthusiasm and is going out. I mean, look at our direction. This is good. I wish we had stock in ourselves.
So just on Wild Apricot, when do we need to get an account? When we get a renewal email?
Yeah, when you get a renewal email, there'll be a link to click, and depending if it's the first notice, then you'll click on it and be asked to create an account, or actually it'll ask you to log in, and I think it'll fill in your email address as a username. You just click the forgot password to create a password that you can remember, and then the three emails that go out. The third one that goes out is when you're 90 days overdue, and it'll say you've got 5 more days before your account is deactivated. And I think at that point, if you click it, it'll just let you renew without having to create an account or to register your email. Register your password. But so the grace period is really 90 days, but don't wait until the last minute, because I had a couple of people who did, and by the time they renewed, their account had been archived, and it's kind of a pain to go back and unarchive their account. Okay. Anything else? All right. Thank you.
Thank you, Spencer.
Let's see. Do we want to do committee reports? Do we have anything to go in? Luck? Board is closed. Mount Wilson isn't open yet. The dates are not, any of our dates are not there. And it's been really, really cold. They're not really having people up because it gets so cold at night, but you don't see the ice on the road. So there's black ice problems up there. So if it's cold at all, they're not open. Question? Okay.
Are there any
Lockwood?
updates on what's going on at Lockwood, or did we get something down in time for winter?
Did we get what done in time?
Did we get everything covered up in time for winter? The new observatory wasn't finished, the last I saw. And I've been under the weather, so I haven't been up there to see what's going on. I just wondered if we got it all covered up in time for the snow.
Yes, we did. Carson shed got reassembled and it got clamped together, and then it got covered because we weren't quite done because we needed to replace the rails that got twisted.
Daryl, I was there for that. That's not what I'm talking about. It's talking about when we were finished, we weren't done, and that's what I'm concerned about. Is that we had the roofs laying on top of the rails, and we were going to try and put covers on, and then all of a sudden, nobody's been involved for a number of reasons. We won't go into that, but I'm just wondering what has occurred to protect the new observatory, even though it's not officially covered.
It is officially covered.
With what?
A tarp.
A bunch of big tarps are covering it, and it's waiting for the weather to come back so that we can take them off and finish it.
Got it. Okay.
So it's been protected since it was finished to the point that it is now.
Okay.
Richard, it was covered up the day after the very next day.
Oh, got it. Got it. Okay. So nobody ever let me know that. I've been kind of worried about that. And all I know is we weren't done, and then all of a sudden we weren't there. So, okay. Thanks, Spence. That's all I needed to hear.
Wow.
Okay. I didn't see, is John here?
No, John's not here.
Okay. All right. I didn't know if he was going to do a short report.
What you want to
Treasurer's
announce?
report.
So John, you want to announce co-chairs?
Yeah, I'm sorry, announce that? Yes.
Yeah.
We haven't had a Lockwood committee chairperson for a while, and we now have a co-chair between Spencer and John O'Brien. So they're going to co-chair the Lockwood committee and continue to take it forward. And it's been updated a lot. I don't know how many people have been there recently or not, but I was impressed with the upgrades and how much better the grounds were and how flat things were. And, you know, a couple of new pads are down, and the big pad for Dobbs. I mean, there's a lot of stuff that got changed there. So, Spencer, is there anything else that we need to update? Any new things?
Did you want to talk about the donation?
I guess I can. Sure. Okay. Another big announcement for Lockwood specifically is a couple of us have been talking to a donor who is very interested in Lockwood. And we've had many conversations back and forth about what kind of donation he wanted to make. So he first just said, well, look, I'm just going to give you $10,000. I don't care what you do with it. It's just, you know, no strings attached, whatever you need. Okay. So that led to some other conversations about Lockwood and what we wanted to do there, and how we were going to use the Carson roll-off shed for the Takahashi. And we thought, well, you know, it's a split roof, you know, shed. Is that really the best thing for the Takahashi that we have that was a donation as well? And we decided that maybe wasn't. So we talked about a different roof for the Carson shed. We can put a PureTech roof on it, but we decided that maybe that wasn't quite enough either. So we ended up deciding that we needed a brand new 10 by 10 PureTech roll-off with automated roof and pier to go in at Lockwood, including the pad to set it on. And our donor has picked up the check for the entire thing to the tune of another $40,000 besides the first 10. So we recently got that, and it's in the works already. I think we've already made the order to PureTech, and it's going to be a few months. It takes them a while to fabricate, put it together, and they take it apart and ship it. And we have a couple of things on the shipping on our end to pick it up, but we'll get the details worked out on that. So I think we have until June, I think, is when the delivery date is. So we have plenty of time to get a pad poured And I mean, I can't tell you how much I've thanked the guy, but he's not, want to be known. So that's great. So big news for Lockwood.
So I'm confused a little bit. Does that mean we're ignoring the roll-off roof observatory we just built up there?
No,
for that purpose?
We're going to completely finish that one and put another telescope and another pier in it and use it for on-site use for people there. We can open it and close it. And also for astrophotography classes. It would be a great place to put cameras on with people inside there and talk about it and have lights on and do things that they need to know how to do and see it. So we can have both observatories. So we will have two roll-off shed observatories, one for teaching and using, and the other for using as well if you're on site. But it can also be used remotely. It's one of the things that the donor wanted to have happen if he was going to put up the money. So it will have automatic roof and control over the telescope. And the software, I mean, there's a touch screen. It's a really, really nice shed. So,
Well,
all right.
Okay.
Daryl, I'll just mention it. Sounds like things are really moving and money's being poured in. That's great. I'm just thinking about in the future, we need to have terrific security there. We don't want to have any problems. I don't know if that's been brought up, or maybe it's been brought up a long time ago. I don't know.
Well, both of the sheds are they're pretty tough, and people don't know what's in them unless they know what's in them, but they probably won't. I'm not sure what to do about that. I think it's probably going to be okay. We can have a security person on site if we need to. I was just at the county a couple of times in the past week asking a lot of questions. So I saw that there's a security person available, something we might have to get a conditional use permit for, or we can have somebody on the lot and stay there.
I think I meant more an alarm system.
Who's it going to alarm? And how long is it going to take them to get there?
Yeah.
How about cameras and video and internet connections?
Well, we have a couple. We have two cameras already, and we can add that,
Okay.
and then we can see people take stuff. Hey,
Guys, one thing to remember, we talk about security, but remember, if we're a STAR member, and which many of us are, we are allowed to go up there whenever we want. We don't have to make a phone call and say, hey, I'm going up, but we have the codes. We are allowed to go up. We go in, we do our thing. So when you start talking about security, it's like, wait a minute, now do we have to present ourselves to someone? I mean, if Al is our security, great. I'm more power to it. But if we start talking about off-site security, we're starting to get into ridiculous levels of what are we doing?
we're not going there. Don't worry about it, Richard. We're not going anywhere near that. We don't need it. Don't get paranoid about what we have on site.
I think these are things that we're going to have to take up in the Lockwood Committee and come up. This is probably not the right forum for it, but the Lockwood Committee is.
I just heard that and I didn't understand where to go with it.
Yeah.
We can put turrets with guns up,
This is probably something for the Lockwood Committee too. But has there been any word on the rest of the user pads, updating them?
Yeah. We're going to have to revisit everything. Yes.
Okay.
That is also in the works. There's a couple of new test pads already there for people to look at and say, do you like this as a model? So that's happened already. So next time, I don't know how that's going to be presented, but the Lockwood Committee will take that up and present that information to people who can use it. The other thing about Lockwood is while I was at the county, got in contact. I have the address of the person that owns the property next to us to the north, and I'm going to contact that person and find out what their interest is in the property, what our interest might be in the property. And the reason for that is that property has a well on it. We need a permanent source of water for that, for the rest of our time there. And we're losing our current source of water, which was the neighbor next door who's been nice enough to fill our tank for the past few years. But they don't want to do that anymore. So looking for another source that's permanent. So I'm working on that in the background. I got the guy's address. I'm working on a letter to him. I don't have any phone number, so I can't call him. So I'll have to wait for his reply. But that's all in the works as well. So, we're moving a lot on Lockwood. It's good. We own the property. If we can get another piece of property, we could expand. Things are going well. It's going faster than I thought. So, anything else about that?
We're good.
Okay. Well, I guess we're on to Jeff then. Tim, did you invite him and want to introduce him?
Hi, Jeff.
Well, I know Jeff too. I see him up in Mount Wilson, but hi, Jeff.
Howdy. Hi. Well, okay. There's the real Jeff down there. There's the picture of Jeff over here. There's a bio of Jeff you can read on your screen and an abstract of his talk. And he's like a real life professional astronomer who still has a job, unlike some of us who are retired. And when I talked about James Webb, all I did was talk about it, but he actually uses it and analyzes the data. And so he has real stuff to say about it instead of what I say. So Jeff, it's all yours. And Daryl, stop sharing your screen so Jeff can share.
Okay, thank you. Despite all of my Zoom practice, last time I gave a talk on Zoom, the slides weren't working for the first 5 minutes and they had to stop me. So hopefully that doesn't happen tonight. Let's see. Okay, so do you see a slide that says pulling back the dusty curtain on luminous infrared galaxies?
Good,
excellent.
Absolutely, you're good to go.
Okay, I'm going to tab forward and hopefully this works. Do you see a picture of a galaxy that says, what is a galaxy?
You are here.
Yes.
Yep.
Thanks, everyone.
We're going to mute everybody, Spencer, and for questions, so we know, everybody knows the rules.
I'll keep an eye on the chat if I can. It's gonna be a little tricky doing two things at once, but I'll do my best. Thanks for having me again. So I'm Jeff Rich. I'm an astronomer at the Carnegie Observatory. So I'm up in Pasadena. You can find me around occasionally at outreach events because I run our outreach and education program. And I'm here to talk about a research group that I work with that studies nearby merging galaxies. But I usually like to start these talks with a little bit of basic background just to refresh my own memory about why it is that we do this stuff, aside from, just wanting to look at cool stuff in space. So, I have a feeling we all have an idea of what a galaxy is. Astrophysically speaking, when I say galaxy, I mean the gravitationally bound system of stars, stellar remnants, interstellar gas, dust, and dark matter. Now, galaxies come in a huge range of shapes and sizes, and this is one of my favorite visual representations of the range of sizes and shapes of galaxies. And it actually has, this is the small version, and in the middle is a mock-up of the Milky Way galaxy, an artistic rendering as it would be seen from above with respect to some other familiar galaxies. But you can zoom out because there's some galaxies that are incredibly huge, both in mass, where the Milky Way is 100 billion stars. The biggest galaxies are about 10 times that. And galaxies that have really long, huge structures like radio jets and tidal tails. So what are we doing here? Well, I think galaxies are neat, and I'm an observational astronomer. I like to use telescopes to look at the universe and see what it is that we see out there and try to understand and explain it with respect to what we think we understand about physics. I just think galaxies are neat, and I want to look at them and understand them. But there are lots of things that we observe when we look at lots and lots and lots of galaxies, as we've done for a very long time now. So there are lots of things that we can measure and compare, and we see, differences in the rate of star formation, the amount of gas available, how many stars there are, whether how big the supermassive black hole is in the center of a galaxy, whether that black hole is actively accreting gas or not, shapes, whether there are young stars, old stars, or a mix of both. And the more galaxies you look at, and the more you look at all these properties, you start to see sort of trends and differences. And there are sort of different ways to approach it. I'm an observer. I like to look at galaxies and try to explain what we see. But there are folks who spend all their time using physical models, both of single galaxies or of forming stars, all the way out to models of the entire universe in a computer to try to explain what we see when we observe the universe. An early example of trying to make sense of the differences between galaxies would be your classic Hubble tuning fork. One of my favorite things about the Hubble type is there's an outreach activity that we do with people of any age, kids and adults. And if you give people pictures of 30 different galaxies and ask them to sort them, they start to find the same kind of trends and patterns, because we're all sort of trained to look for patterns, and they don't recreate the Hubble tuning fork necessarily, but they notice, well, some of them are round and some of them are blue and some of them are yellow. And it doesn't take long for people to start asking, well, they didn't start this way. How did they get that way? Does one kind of galaxy change into another? And that was a question that was asked early on. Well, there are, it turns out, lots of different trends when you look at lots of galaxies. This is just an example of some very broad and important concepts in galaxy formation and evolution. One of them is, on the far left, is a luminosity function. That is, how many galaxies of a certain brightness do we see? And we have observations in blue. This is just a cartoon version. And the red line is what the theorists predict based on what we think we know about how the universe works. And the lines don't the lines don't match, and we have some explanations for that based on physical processes, and we're still figuring that out. We also see a correlation when you look at really big, massive galaxies compared to somewhat smaller galaxies. The central bulge and the black hole mass seem correlated. So galaxies, the bigger the galaxy, the bigger the black hole. Why is that? Well, you would think that as you build a galaxy, the black hole should be getting bigger at the same rate. Some of them don't, some of them do. Another thing that we see is galaxies seem to be split into a population of redder galaxies with old stars that are not making new stars, and galaxies that are actively making new stars at varying rates and of different sizes. The blue and red galaxies are sort of a good way are sort of a way that astronomers use to keep track of whether something is making stars or not. And if a galaxy is actively making stars, it's slowly building itself bigger and bigger. You can think of, for instance, the Milky Way is about 100 billion masses, suns worth of stars, solar masses. And it's making about one more solar mass of stars a year. So if you wait 100 years, it'll be 100 solar masses bigger, 1,000 years, 1,000,000 years, and so on. But that might change over time. And, you might have a galaxy. Generally, we think galaxies get bigger. They don't lose colors, or excuse me, they don't lose mass. But sorry about that. They might start forming stars again and turn blue as they get bigger. They might grow bigger by merging. There are lots of different ways to grow galaxies. So when astronomers are looking at galaxies or looking at many galaxies, they're trying to answer basically, how do you create the ensemble of galaxies that we see here when we look at the universe? Okay, so the big questions are sort of, how do galaxies grow and change with time? What causes galaxies to stop and start forming stars? And how do we observe that happening and compare it to people who are trying to model the universe? one of the most important things in studying galaxies and stars and anything is tracking gas. If galaxies don't have a source of gas to make new stars, they'll stop making stars and stop growing. If you use up the gas or you remove the gas, star formation will cease, and your galaxy will basically be done until it finds a new source of gas. We can look to places in the Milky Way to try to understand the details of that process. Since galaxies are so distant, it can be tricky to figure out the detailed physics of star formation, but luckily we live in a galaxy that's actively forming stars, so you can look to places like the Pillars of Creation or other star forming regions. This is not what I do, but it is something that a lot of folks are focused on. And I had to throw the JWST picture in there just because it's beautiful. And I'll be talking about JWST data of galaxies, but one other thing I wanted to mention is we think that there are these really sort of violent processes that can change the course of a galaxy's life, and they can stop and start over time. One is sort of, if you have an intense burst of star formation, you can end up with so much energy input into the interstellar medium from supernova, from young hot stars, that effectively all of this energy and momentum pushes gas around. An example of that would be M82. When you look at the image on the right, this is our nearby Cigar Galaxy, and the red light is warm gas that's being heated up and pushed out of the galaxy in a bipolar outflow. The other source of what we call feedback, something that can change the amount of gas or push it around, is an actively accreting supermassive black hole. Gas accreting onto a supermassive black hole can heat up, give off a lot of energy, and also drive jets or winds. These are sort of detailed physical processes that are for folks who model star formation and galaxy formation. They're sort of inputs to the model that change the amount of stars and gas and dust and change what your galaxy will look like if you wait a few billion years. So understanding these processes by looking at examples of them in the universe is really important. So, to get to the punchline, I like to look at these really nearby ultraluminous and luminous infrared galaxies. These were discovered in the 1980s by the first infrared satellite, and they're galaxies that are incredibly bright at infrared wavelengths. So they are, giving off most of their light at infrared wavelengths, and that IR emission is dust that's being heated by really, really strong, intense star formation and actively accreting black holes. So if we want to go looking for these really important physical processes to study how they work, these LERGs and ULERGs might be a good place to look. And I'm going to say they are a good place to look. An example of one of these galaxies is on the right. It's one of my favorite. Telephone number is VV114. It has a bunch of other names. But in the local universe, most of these luminous infrared galaxies are actively undergoing a merger that's really driving the gas around. So when I say gas and dust, gas is any matter in a gas phase. It can be that can mean it could be hot. It can be hot. It can be hot gas. Can be molecular gas. Dust is essentially it's dust like you might think of it here on Earth. It's not that different. There are many different kinds of dust. It's silicate particles, minerals that in a region where the interstellar medium is cool enough, basically chemistry starts to happen that causes the elements available in the interstellar medium to create chemicals, to create minerals. And if you wait long enough and you have the right conditions, those chemicals and minerals can condense and create larger and larger dust particles. And if you're in the vicinity of a protostar, you might end up with something like a protoplanetary disk, and so on and so forth. But dust is sort of everywhere we look in the interstellar medium. you can just think of it as basically small grains of minerals and that have formed in cool interstellar space. Just by looking at the Milky Way with your naked eye in a dark sky, the dark patches in the Milky Way are lanes of dust in our own galaxy. So when I'm talking about dust in these galaxies, I'm talking about not dust in the Milky Way. That's, if you're trying to look up and look at distant things, dust can be a problem. But dust in these galaxies is both already there and being formed during this really interesting, violent process of a galaxy merger. The whole process of merging takes about 1 billion years, a few 100 million years. And if you take two gas-rich spiral galaxies, this whole process will create a lot of stars in a very short period of time. And we think it's one way to build a massive elliptical galaxy after the whole process is over. This is just one way. There are other ways to get there. And a galaxy can undergo many mergers, both what I'm talking about are called major mergers, sort of two equal mass galaxies that have a lot of gas that are able to make new stars. Something that would be not a major merger would be an example of that would be the Milky Way and the Magellanic Clouds. The Magellanic Clouds are dwarf galaxies that are merging with the Milky Way. They're not drastically changing the shape and morphology of the Milky Way, but the Milky Way being much larger is going to rip the Magellanic Clouds apart. When you take two equal mass galaxies and throw them at each other, the tidal forces that both galaxies feel as they pull and tug on one another basically sort of rips the galaxies apart and creates these really interesting fuzzy train wrecks and can leave you randomizing all the orbits with a galaxy with no gas left to form stars, either because it gets rid of the gas or uses it all up. So we think this is a really important process that can really drastically change how galaxies look. So it sort of behooves us to look to nearby mergers and study them in detail. And just, many of you already know this, but this is going to happen to us in the Milky Way, but not for about 5 gigayears, so you don't have to worry about it. But the Milky Way and Andromeda will undergo a major merger. They will probably look a little bit like one of these luminous infrared galaxies during the process, and we might be left over with a big merger of the two galaxies that's just a quiet elliptical, which currently the name I've seen is Milkomeda, which leaves a little bit to be desired. So we've got a few billion years to figure out a better name. So, to get to the fun part, we study these galaxies because they are sites of really intense transformation that can help us understand the broader picture of, the thousands and millions and billions of galaxies as we observe them throughout cosmic time. So what I'm talking about is we like to take a few of these nearby galaxies and really zoom in and study them in great detail to try to answer the questions like, how do you build a supermassive black hole? How did we get galaxies to look like they are now? And we had a successful proposal before JWST was even launched to look at 4 of these nearby merging galaxies with what is called early release science program. Essentially, the data that we were asking for would hopefully be interesting and useful and be a way to test JWST after it's launched and to help work out the kinks in all of the software pipelines and data analysis programs that Space Telescope in Baltimore have been working on for years and years and years. So when all of us first saw the beautiful images that JWST made public this summer, a few days later, all of the data that had been taken so far as part of these programs was made public to the world. So we hit the ground running and we're rapidly trying to analyze the data, reduce the data, and see what we we had some guesses about what we would see. So we didn't write the papers ahead of time, but we were trying to sort of tease out what would be the interesting science. And that sort of led to 8 papers on 3 of the objects. And that's because as JWST goes around the sun, it can't look at everything, right? It's sort of limited to a certain patch of the sky because it can't look towards the sun. So one of our 4 galaxies was not observed until around this Christmas, NGC 3256. The galaxies that were observed early on with all of the instruments that we wanted to use were VV114 and NGC 7469, and I'll talk a lot about them. But suffice to say, all of these targets we knew were going to be really interesting, and JWST let us look at them in a completely new light. And I put the pictures of my 7 colleagues who led the first 7 papers that are not the one that I led. I didn't put my picture here. You can see me in the corner. We're an international collaboration. Aaron Evans is a professor at University of Virginia. Lee Armis works at Caltech IPAC. Thomas Lai is his postdoc. Vivian Yu is a researcher at UC Irvine. Thomas Bond and Hanai Inami are at Hiroshima University, and Sean Linden is a postdoctoral fellow at UMass Amherst. I really was hoping one of them would want to speak to you because I love to give public talks, and I'm glad to be here tonight. But they're all really great researchers, and they would do, I think, a fantastic job talking about all the work we've done. So I'm going to do my best not to trip over any of the work they did, and they were very kind and sent me a lot of the slides you'll be seeing. So what did we do with JWST to look at these really interesting nearby galaxies? We used 3 instruments on JWST. One is NIRCam, which took images in near infrared light. So the numbers you see there are wavelengths and microns. Near infrared is just beyond what your eye can see. Red light, is about 0.65 microns. Your eye sort of gives out around 0.7, I think. So the great thing about JWST is it not only had an incredibly massive mirror, but it had a wide wavelength range. So it can see near infrared light as well as mid-infrared light. So we also took images with the MIRI mid-infrared instrument imager at longer wavelengths. And we have spectra, which from 2 different instruments, NIRSpec and MIRI, essentially allowing us to pick apart the light at these wavelengths that most of which are not visible from the ground. So this is science that could only be done with an infrared space telescope, especially once you look at wavelengths longer than 2.5 microns. I use one of these galaxies as an example of one of these really extreme cases of the difference between the visible light and the infrared light. This is 2 Zwicky 96. This is HST, ultraviolet and visible light. And before JWST came along, there was a amazing telescope called Spitzer that helped us learn a lot about these galaxies and sort of, gave us a hint at what we would be seeing with JWST, as Tim knows. Yes, absolutely. Thank you, Tim, for helping make this telescope happen, because it helped us plan our observations. But to really highlight how far we've come, this is a Spitzer. The red blob that you see there is a Spitzer image at 24 microns. So all the light at that wavelength, at those infrared wavelengths, is coming from something completely different from all the visible light. If you look at shorter wavelengths with Spitzer, 5.8 microns, you do a bit better. The resolution is a bit higher at shorter wavelengths, but we still don't resolve whatever is happening. Again, all of the infrared light in this galaxy is almost all of it is coming from something in that really compact space. There's still a bit of infrared light coming from the rest of the galaxy. I'm not saying there is none, but the vast majority of it is coming from that blob. And once we had JWST data, that blob turns into a bunch of little blobs. So you zoom in so you can see the difference. I mean, we went from unresolved. We could learn a lot about things by measuring how bright that unresolved thing was. But JWST, you're starting to pick out individual clumps of star formation and clusters and all sorts of cool stuff. So we now have almost HST-like resolution at these wavelengths, which if you're used to looking at infrared light is just spectacular. Just take my word for it. The galaxy that is one of my favorites that was taken early on is VV114. These are examples of some of the images that we got with JWST. On the left is an HST image, so it's visible light wavelengths. And the image on the right is near infrared wavelengths. And there's a couple of things that pop out right away. One is that the brightest thing at near infrared wavelengths, the thing with all the diffraction spikes, is nearly, it's essentially not there, even at almost near infrared wavelengths with HST. So again, we knew from Spitzer, most of the light in this galaxy was coming from a buried source where there is so much dust that all of the visible light is scattered or absorbed or lost. And the other spectacular thing about JWST that I already harped on is that you really get you get a lot out. It's not just, oops, sorry. There we go. Okay. You get mid-infrared wavelengths and near-infrared wavelengths. And so you can see the images here are telling a story that is different at all different colors of light, that tells you about cold gas, warm gas, hot gas, dust, and we can put all of that information together about the interstellar medium, about star formation, about the supermassive black hole to really drill down on what's happening in these galaxies. So the image on the right here, the bluish, this is not my favorite color scheme, but it looks beautiful. The bluish light on the right is tracing something called polycyclic aromatic hydrocarbons. And I'll come back to those later, but it's essentially these long chain hydrocarbon molecules. I've seen different ways of describing them. They're, I saw one person who studies these said after you use a grill for a while, all that soot that you scrape off would be similar to polycyclic aromatic hydrocarbons, PAHs. Essentially, it's tracking chemistry that's happening in space, and the properties of those molecules tells us something about the interstellar medium that they live in. And just to, again, really highlight how far we've come, on the left is an image of this same galaxy with Spitzer at sort of similar mid-infrared wavelengths. We learned a lot from Spitzer, but the resolution that you achieve and the depth you achieve with JWST in a short period of time is really revolutionary. Oh yeah, somebody asked about little red galaxies around VV114 in the near-infrared picture. Absolutely, that was one of the other really cool things. As soon as we started seeing pictures off of JWST, every picture has a whole bunch of background galaxies that are much more redshifted. So, we're really interested in studying the thing in the foreground, but all of those red things in the background are background galaxies. And, these are relatively short exposures because they're so nearby and bright in the infrared. And you still get a whole bunch of redshifted galaxies that just are not even there in the Hubble Space Telescope image. So I don't doubt that people are right now looking at the archive that's already available and trying to think of, there are people who want to study all those background things that I think are really exciting, but is not what I study. Let's see, I accidentally annotated my image. There we go. If anybody noticed the little red dots, sorry about that. Oh. Okay, So here's something that we could do even before we had the spectra, just the images. You know, they look spectacular and beautiful when you combine them in a 3-color image, but you can do science with the images. So the cool thing is you can drill down into that core. We took special data that's really short exposure times. That's different than the full array image. And when you look at the central part of this galaxy where all the infrared light is coming from, we actually see a couple of really bright sources. And the cool thing is you can tell something about them just from the image, just by the colors, because we took images, you remember, at multiple wavelengths of light. Just by looking at the relative brightness at those different infrared wavelengths, we could tell we were pretty sure that this very bright core to the north, to the upper left, is probably a buried star cluster that's very, very bright and massive and very compact. And we were pretty sure that the thing on the lower right is probably a black hole that's actively accreting mass. And this is something that the previous infrared telescope just didn't have the sensitivity or the resolution to measure. And as I said, you know, don't worry too much about this figure, but we're building on a legacy that the Spitzer Space Telescope built. So this image, all those colored dots are measurements of single galaxies, of the relative color of ratios of these colors, taken with the Spitzer Space Telescope. So we have some idea about the physical processes that these infrared colors track based on, you know, Spitzer. And all of the black dots are individual clumps of gas and star formation in this one galaxy, where with Spitzer we would have essentially had one data point. You have a whole slew of information that wasn't there before. And because HST has such good resolution, you can drill down and measure the properties of individual star clusters. So another astronomer in our group, Sean Linden, he is really interested in counting how fast and how massive a galaxy is making, in this situation, is making stars. And so what he did is he went and pinpointed on the lower left, you see these on the lower left panel is a Hubble Space Telescope image. On the lower right is an image taken with JWST at near infrared wavelengths. And there are star clusters that are completely invisible to HST. And they were just not known. So to get an accurate measure of the star formation, we really needed JWST to track that. On top of that, these really embedded these sources that were undetected at visible light wavelengths, are often the youngest star clusters. So if we want to know what the newest stars look like and how big those clusters are as you're building these new stars in emerging galaxy, this is the place to look. And so Sean he did these quick measurements to get some useful information out to the community to think about what else we could do. And he's now doing a detailed follow-up to look in great detail at all the clusters and all of the galaxies that we've looked at so far. And the coolest thing, I mean, the thing that's really amazing to me, on the left is a plot. Again, if you don't worry too much about exactly what you're seeing there, essentially on the y-axis and the x-axis is a measurement of the color. So to the left is a bluer color and to the right is a redder color. The redder colors are caused by dust extinction, dust blocking light, as dust preferentially blocks bluer colors of light. So it makes your galaxy clusters or your stars look redder, or your star clusters or your stars look redder than they would if there were no dust. If there's enough dust, you can't see them at all at visible wavelengths. And so all these little clusters, these little gray circles on the right, are brand new, never before seen star clusters that are about 1 million years old, which, you know, is barely a baby when it comes to star formation. There is another group called PHANGS. It's an acronym PHANGS. I don't work with that group, but they're doing the same sort of science in very nearby galaxies that are much less intense and highly star forming situations. So they're going to do doing a lot of comparison with what we see in these merging galaxies to see how it compares in like a more calm star forming galaxy like the Milky Way. So we're still finding that out. It'll be coming soon. And I threw this image in there because it's brand new. As I said, Sean is working with all of the galaxies now, and this is NGC 3256. So this is really interesting. It's going to be exciting to see, aside from just we're seeing these clusters for the first time, what that means for how you build a galaxy during the merging process. So, stay tuned. I will come back to VV114 because it's a real smorgasbord of what's happening in emerging galaxy. But I wanted to turn to the one other source that we looked at very early on in this program, and that's NGC 7469. It's one of a pair of merging galaxies. It's the one on the bottom of these two galaxies here. And we pointed JWST at this galaxy because we knew for sure that it had actively accreting supermassive black hole, an active galactic nucleus that was visible at visible wavelengths. And we knew there was this interesting ring of star formation around that supermassive black hole. And so what we wanted to see was what we were missing at visible wavelengths and unique chemistry unique physical processes and chemistry that only JWST can trace in great detail. We had, again, hints of what was happening with Spitzer, and we knew we were going to get a lot more info once we pointed JWST. So the first work that was done, I don't want to say easy because it's not easy, but the quickest analyses that were done with JWST data, and that's the case for our team, were simply looking at the imaging data that were available. And the first images that were available were these mid-infrared and near-infrared images. And postdoc Thomas Bone wanted to look at the star formation around this AGN. Because we think in some galaxies, an active galactic nucleus can have an impact. It can either, in some cases, we think it can make it harder for stars to form. We think it can compress gas and cause star formation. There are cases where the amount of feedback varies. So it was interesting to look at what's happening around this thing. And I wanted to point out the image on the left is a wide field near infrared image. The image on the right, and sorry I forgot to label this. The image on the right is a zoomed in region. And again, those little things that look like stars are star clusters. And the fuzzy blob in the middle is essentially the AGN is so bright that even with our short exposures to study the stuff around the AGN, we blew out the center of this thing. And that interesting pattern is just an imprint of the telescope's mirrors once it reaches the detector. So to do analysis, you sort of mask that out and don't worry about it. We're looking at all the stuff around that in this case. So Thomas looked at all of these star clusters, and again, on the top are near infrared images, and on the bottom are mid infrared images, and that's the difference in the image is primarily driven by the resolution of JWST. At those longer wavelengths, it's slightly lower resolution. So I've been waving my hands and saying short exposures because I went and looked at all the numbers earlier. It depends on the galaxy, and it depends on the mode. So we actually, the way that infrared detectors work is they essentially take many samples and calculate a rate. And you have to read the detector many times to do that. So you can take incredibly short exposures if you're only reading a small piece of the detector. So we did both what's called a subarray, just the very center of the detector on the very bright nuclear regions of these things, where the total exposure time is similar to a stack of many exposures. And it's called up the ramp sampling if you want to read more about how that whole process works, how these infrared detectors, near infrared and mid infrared wavelengths figure out brightnesses. But essentially you're taking, in the case of the subarray and full exposures, it's either tens of seconds or hundreds of seconds total to get to these beautiful images, because these galaxies, as I said, they're very bright and nearby. Very different from the other amazing science that's coming out looking at very, very distant galaxies. We need the infrared wavelengths in our case to see through the dust and to do chemistry that we couldn't do at visible wavelengths. For those distant galaxies, your light is being shifted so far to the red that they're just not visible at visible wavelengths. So I show these pictures because I think they're just beautiful, and they show how you can tease out information about how many clusters are there, what their ages are, how much dust there is based on how red they are. But the real physics of what's going on you get from spectra. And we had some information before from Spitzer Space Telescope. Spitzer had a spectrograph. There's also a slightly shorter wavelength spectrograph called Akari, that's 2 to 5 microns. So we had some expectations and work that's been done over the last couple of decades to prepare us for what we might see at these wavelengths with JWST. And this is an example. On the left is the slit, essentially all of the light added up in that blue box is being used to create this spectrum, which is how bright the object is at these different wavelengths of light. And all those wiggles and bumps and troughs are all different features that track a whole bunch of different processes and a whole bunch of different species, and I'll get to them. So, oh, there we go. This is the red spectrum is the JWST spectrum. So not only do we gain in sensitivity, but JWST, the spectrograph, is a much higher spectral resolution. We are restricted to this red box on the left. It's only that central region all added up to make that red spectrum. You'll see that it generally matches what we already saw with the Spitzer Space Telescope, but you're able to resolve different spectral features that are generated by different things, different molecules, different elements in incredible detail. So that helps you, the fact that we can measure these different species, that we could not do at this resolution before, sort of unlocks the ability to look at, things we haven't even done yet because it's new, and to measure the velocity and the density and all these other physical properties that we did with Spitzer, and this is mind-boggling to see the difference. The lower right is a couple of features, and you can see Spitzer just it did a heroic job of observing these, but just didn't have the resolution. And the other great thing about JWST is you don't just get to add up the box and get a single spectrum. In that box, we have what's called an integral field spectrum. So all of the light, you can break that whole box up into a bunch of little squares, pixels, and each one of those pixels has a spectrum. So you can make two-dimensional maps of all these different features that we see at near-infrared and mid-infrared wavelengths. So this is an example of a PAH, one of these polycyclic aromatic hydrocarbon features. PAH features are usually coupled with the wavelength at which they are observed, in this case 6.2 microns. And in this case, Thomas Lai, who's a postdoc at Caltech at IPAC, was really interested in studying the dust and the gas around the black hole, not the black hole, not the stuff right up against the black hole, the accretion disk, but the dust and gas, say, a few hundred parsecs away. Because we think, even though that's a fair distance from the supermassive black hole, we think that it can have an effect on the gas and dust at that distance, or even at greater distances. So what Thomas did is he made a map, but he also, this was very early on. We were trying to do what we could with the data very early on, which was sort of, we were handicapped a bit by the pipelines for reducing the software were still being developed. They are still being developed. They're doing a great job, but some kinks are still being worked out. So what Thomas did is extract a bunch of all these circles. He added up all the light in that circle and looked at the spectra and compared them to see how the dust varies in this ring around the supermassive black hole, the AGN. And you can go and look at his paper and look at all of these features and look at the variation. But Thomas painstakingly fit and picked apart all these different features using a new piece of software that he's been working on with some of our team that is really remarkable. It basically uses what we think we know about the physics happening in these regions and attempts to fit all of the different physical processes, the dust, the dust, which is emitting infrared light, the elements that are creating emission lines. There are absorption features and emission features caused by dust. And then you can use all that information to look at what's happening to the gas and the dust. In the case of this galaxy, Thomas was interested in looking at these PAH features at 6.2 microns, 7.7 microns, and 11.3 microns because they trace different sized dust particles, essentially. And he made this nice cartoon. The x-axis is a ratio of two of these features, and the y-axis is a ratio of two of the features. And as you go to the left, as the ratios increase to the left, you're tracing larger and larger dust grains. And as you go from top to bottom, you're looking at dust particles that are ionized and molecules that are ionized. Essentially, the dust is reacting to what's happening around it. So you would expect to see different dust properties depending on what's impacting the dust. And that's what Thomas saw. Essentially, the thing that he found is that the closer you got to the supermassive black hole, it seemed like you were seeing larger grains, bigger dust grains. Why that is, we're still figuring out. Could be dust. The dust is being affected by the physical processes around it. So smaller grains are getting destroyed or larger grains are getting formed. I was hoping Thomas would be able to talk to you all tonight because he is the expert at these. But unfortunately, he was on his way to his family in Taiwan. So he very kindly gave me these slides. But suffice to say, I'm hoping he'll be able to talk to you all someday because he's continuing to study the dust in great detail in these and really see how does the AGN and how does the star formation change the dust. Because one of the things about dust that's really useful in the interstellar medium and in galaxies is that it is a way to help gas clouds cool and condense in a positive, in a sort of loop of positive feedback to help star formation carry on. Sorry about that. Now, another group led by Vivian Yu at Irvine was really interested in trying to make early two-dimensional maps of the environment around this black hole. So not just looking at the dust, but looking at the gas and at different phases of gas. So she gave me these helpful plots that are really similar to the ones I just showed you, but she also looked at the these different species. In this case, you can see iron 2 as on the left. That's singly ionized iron atoms. In the middle is molecular hydrogen feature, and all these different. I almost forgot argon 2. Essentially, what you can do is map all these different features, measure their strengths using a 2D map, and then it tells you something about what's happening in the interstellar medium. On top of that, we have some information about how the gas is moving because we've resolved these individual lines. And so she made this nice little movie. Only plays one time. But what you're seeing on the right as that movie plays is the individual pieces of an emission feature that trace the velocity of the gas. So you can measure how fast and in what direction the gas is moving to look for things like galactic winds, to look for things like weird rotating disks. And so that's something Vivian did very early on with these data. And what she found is using one of these really high ionization potential lines that we only see in the presence of, we only see in distant galaxies in the presence of you have to have really high energy processes to ionize these lines. And magnesium 5 is an example. We call them coronal lines because here in the solar system, we see them in the corona of the sun where you have really, really hot gas. So you can strip electrons away from atoms and get things like iron 13. In distant galaxies, we typically only see these atoms missing lots of electrons around the accretion disks around supermassive black holes. And so when you see these lines, they're telling you something about the really hot gas associated with that supermassive black hole. And what Vivian saw and her team saw was the kinematics, the velocity of that gas was a little different. And it was different when you looked at different portions around the supermassive black hole. So what they think they saw was inside of that star-forming ring, they found an outflow, sort of gas being driven out of the central region by the active galactic nucleus. And all this is very quick turnaround research to share with the community. So she and other folks on her team are now trying to do a more detailed model to measure what is the total impact of that outflow and how will that change the future of this galaxy. Another person on our team looked in great detail just at the black hole to really see what's going on right in the center. And he also measured kinematics and sort of found a similar result and measured a mass outflow rate, though with some uncertainty. And one thing that's interesting is when you look at a spectrum, I've been showing you lots and lots of spectra, and there's a whole lot going on there. But on the right image, just the x-axis is wavelength from 5 to 25 microns, and the y-axis is brightness. And just the way that the red spectrum is just the nucleus, right where the black hole is, and the blue spectrum is all the light added up from the star formation, as well as that black hole, the accretion disk, and they look very different. And that's because as you drill down to where that supermassive black hole is actively accreting, one thing you see is these bright coronal lines, these high ionization species like neon 5 and neon 6 that you don't see in just star forming regions. But you also start to lose these PAH features that Thomas was really interested in studying. They basically disappear. You smooth the spectrum out, and we think that's a combination of dust being destroyed and dust being heated and washing out the signature of those features. It's sort of something we knew this from Spitzer, but we were able to separate out and study in great detail in a way we never could before. And the interesting thing in this case was you can use JWST to look at all of these different features, and there are many, many features. In this case, I'm only talking about the mid-infrared light so far because those were the data that we had at the beginning. And you can see the different kinematics. So the gas is moving differently if you look at molecular gas versus hot gas versus warm gas. And warm and hot and cool are all relative. Cool gas is typically a few hundred Kelvin. Warm gas might be a 1,000 Kelvin, and hot gas can be tens of thousands of Kelvin. Depends on what kind of astronomer you're talking to. So the nice thing about NGC 7469 is I was able to share with you, we see these features that are characteristic of an AGN, and we, these coronal lines are something that astronomers use to look for active galactic nuclei when they're doing surveys of many, many galaxies. And it's something that astronomers who are counting and studying very distant galaxies with JWST, they will be using JWST to look for those features even as they're redshifted. So those features are also present at near-infrared wavelengths. And I haven't talked about near-infrared spectra yet, and I'm going to, and that's because we weren't able to look at those spectra essentially until November, because of the sort of delay in the pipelines and calibrations. And we see a lot of those coronal features at near-infrared wavelengths. And the great thing is, if you are interested in counting how many black holes are actively accreting, you can look for those near-infrared wavelength features at mid-infrared wavelengths as you look at more and more distant galaxies. So we're interested in measuring the near-infrared features in nearby galaxies so that folks looking at distant galaxies can go, okay, yeah, we see the same thing. It's pretty similar, and we can calibrate it against those nearby galaxies. So I've come back to VV114 at the end here because this is the galaxy that I ended up studying and being asked to look at the spectra. And it did not did not present as clear a picture as NGC 7469, where we had an idea of folks wanting to study the star formation in the AGN. And we weren't even sure if there was an actively accreting black hole in this galaxy. Previous studies had said there might be. So we thought there might be one. So the first thing we did is, I mentioned these images, we looked and saw, okay, well, it looks like there's two really bright cores. We don't know if there are two if there are two nuclei there, but we think one of them is a black hole, actively accreting black hole, maybe. So when we looked at the spectra, we did the same thing where we looked at a whole bunch of different regions, including these two bright cores, and tried to look for these signatures of an actively accreting black hole, these really high ionization coronal lines, and we didn't see them. We didn't see them anywhere, and we didn't see them where we thought there would be a black hole. So someone asked about using optical interferometers like CHARA. That's a really good question. In this case, because the galaxy is so dusty, optical wavelengths, you sort of can't see what's there. However, you can use sub-millimeter and radio interferometry. So there has been a lot of data taken already with ALMA. So a lot of what we were expecting to see was based on observations at sub-millimeter wavelengths, which have the, approach the resolution, and radio wavelengths, which approach the resolution of JWST. But they don't tell us the whole picture because they're usually tracing cooler, denser gas. It's actually useful to have both all of these measurements at all wavelengths because it allows you to trace the cool, dense gas in the ISM, the warm, it's less dense gas, the very hot gas. So even though we can't use optical interferometers, we absolutely have been looking at other interferometric data to achieve, near the same resolution, just at longer wavelengths. And that actually led us to believe, well, there was a group that said one of these cores was a AGN and the other wasn't. Our data said the opposite. And the mid-infrared spectra were kind of ambiguous. We didn't see this clear feature of an accreting black hole in either core. What we did see is lots of diffuse PAH emission, and that's sort of in the image and in the spectra that tells us something about the amount of star formation and how photons are leaking into the interstellar medium. To actually do the detailed work of seeing what's going on physically will require detailed modeling of the spectra, and we're just getting the software to get to that point. One other thing that we saw is this northeast core, this bright thing, the upper left. So the thing that's labeled A is I keep saying northeast. It's the one of the bright cores. It has an incredibly deep silicate absorption feature. So if you look at that red squiggly line, it's got a big deep trough that's centered at about 10 microns, and that's labeled. It's caused by silicate dust absorbing preferentially at those wavelengths. So if you see a deep trough, there's a lot of dust there, and that whatever's behind that dust is deeply embedded. And I mentioned that these PAH features tend to get weaker compared to the continuum. If you have one of these AGN, like we saw in NGC 7469, the core that we thought might be an actively accreting black hole, the mid-infrared spectra indicated it probably was an AGN, but we didn't know what was going on. We didn't see the coronal lines. There might be some interesting thing going on with the geometry. So at the end of the day, what we ended up doing is it took me so long to get these data together and to try to figure out what was going on that in the meantime, the team at Space Telescope had updated the pipeline, and we were able to include the near spec data. So we looked at these two bright cores and we compared the near infrared spectra with the mid-infrared spectra. Now, the first thing we were hoping to see is some of these coronal lines at near-infrared wavelengths that might be brighter than at mid-infrared wavelengths. And we didn't see them, but we saw a clear signature of an AGN. These dusty features are gone in at near-infrared wavelengths, and the spectrum at near-infrared wavelengths tells us there's an AGN, an actively accreting black hole there, but we're still figuring out why it looks the way that it does and doesn't have these other signatures. And the great thing is this big wiggle at 3.3 microns is something that folks who study distant galaxies are using to track star formation in distant galaxies and to track actively accreting black holes in distant galaxies. So we're hoping that by sharing these data and then following up with more detailed studies, other folks who are studying distant galaxies can compare what they see with what we see in the nearby universe. There's also some really interesting molecular absorption features that another student is following up on. These wiggles and squiggles off to the right are all real absorption caused by carbon monoxide features. And there are lots of other weird things going on that we are, I say we because I'm not the expert at measuring and studying these molecular absorption features, but we're drilling down and figuring out the physics of what's happening in that other core where it looks like there's, I think we measured about 3 or 4 solar masses of star formation a year crammed into no bigger than 100 parsecs. You're taking all of the Milky Way, the amount of star formation that's happening in the Milky Way, cramming it into a tiny space and multiplying it by a few. So there's something really interesting happening, and we're just going to figure that out as we take the time to really drill down and physically model these data. I've gone on way too long. I'm happy to take questions, but I know it's getting late, and I wanted to let you all know there's a new NOVA special or NOVA episode on February 22nd that's going to highlight a lot of the new results. You can hear the folks who actually did the work hopefully talk about some of this. I haven't gotten to see it yet, so I don't know what ended up on the cutting room floor, but one of our researchers is at least in the preview, so I know he'll be there. So check it out if you want to know more, and thank you for letting me talk for so long.
Great, Jeff. Thanks a lot. Let's take questions for at least 5 minutes or so, though. If there's any questions. Everyone understood everything, right?
I tried to get to everybody in the chat. I know there was a lot of technical stuff there. I appreciate you all. This is the first time I've given this talk, and I appreciate you bearing with me. I have a sick toddler and a 6-week-old kid, so I kind of threw it together pretty quickly.
I have one question.
Go ahead.
Yeah. Is it possible that the reason the bigger dusts of grain are closer to the black hole that because of gravitational pull, because they're bigger mass?
That's a good question. I think I don't know the answer to that off the top of my head. The things that I have read about dust grain processing, you tend to get bigger or smaller grains either in a situation where you have shocks as some mass is driven through the interstellar medium, as some shock wave is driven through the interstellar medium, it tends to preferentially destroy smaller grains. So that's one of the main reasons typically given by folks who model this. The other thing that can happen is these dust grains form just, in the star forming regions. And I think they look different depending on the UV radiation field. So the mix of star formation and really high energy photons that are given off. In this case, the gravity is the tidal forces are really whipping things around so much that what it has done is throw these all over in sort of a mess in a way that looks different from nearby spiral galaxies. There's these beautiful images of these features in between the spiral arms in like the Whirlpool galaxy that have been released. Yeah, I need to read those papers. I've just looked at the pretty pictures and press releases so far.
Okay, let me remind everyone to enter for the drawing at the drawing at the end. I just put the link up again, and if there's no more questions, we can go ahead and end Jeff's talk, and if we can do the drawing, and if there's if you want to stay and there's time at the end. We'll probably be about at the end anyway. All right.
Andrea Scarlett had a question.
Great talk, Jeff.
I'm sorry, say again. Who had a question?
Andrea Scarlett had a question.
Andrea, go ahead.
Oh, I see it in the chat. Two supermassive black holes in the Milky Way. So what happens when you take two supermassive black holes and merge them? That's a good question. I completely forgot to mention the fact that when you have two galaxies merge, we expect, though, the supermassive black holes at the centers of both to eventually merge as well. So one way you build these supermassive black holes is by taking them and throwing them at each other. The LIGO, is able to detect mergers of solar mass black holes, so things that are a few solar masses or smaller, tens of solar masses. These really supermassive black holes require a gravitational wave telescope that is larger than the Earth, essentially. So there's designs for a gravitational wave telescope called LISA that is supposed to be an interferometer in space that will be able to detect the mergers of these supermassive black holes and inform the people who are trying to measure how quickly do you build them and how often do the mergers happen? So that's something we're looking for in the future for sure. And during this merging process, the solar system, well, at that point, the sun will be a red giant and the Earth won't be around anymore. But the stars, there's so much space between the stars that essentially, if you do the math, when the Milky Way and Andromeda merge, you'll get about one stellar collision for the whole process. Because there is so much space in between them. What really happens is the stuff might get flung out to great distances and the gas and dust whack into each other. But thanks. It's great questions. Thank you.
I have a couple of quick questions, Jeff. First of all, thank you. That's great presentation. We appreciate it. Is the James Webb Telescope operating 24 hours a day?
That's a good question. As far as I know, it's not limited in time like the Hubble Space Telescope is, where it's going around the Earth. So as far as I know, they're constantly taking data. They're limited in where they can point, and they may be taking calibration and engineering data instead of science data. But yeah, that's a good question. I'm going to ask my colleague who works over there if there's any downtime and why. Yeah.
Okay, thank you. The other quick question would be, our universe is expanding. Why is it that galaxies would collide? Like, for example, the Whirlpool if we're getting larger.
No, that's a question a lot of folks ask, because how can you reconcile those two things? And essentially it comes down to scale. Eventually, if things are close enough that they, in the local universe, we're close enough to Andromeda that it's actually blue shift, that it's moving towards us. The Hubble flow at the distance of Andromeda, the expansion of the universe right now, is not so much that it overwhelms the gravitational attraction between us and, the Great Attractor or the Virgo cluster. It's sort of at this time in the universe, once you get to a far enough distance, we would never merge with something beyond a certain distance, because it is so far that the expansion of the universe overwhelms it. And at some point in the future, that would be the case. Essentially, you can imagine eventually all the structures that are close enough will condense and merge, and things that are far enough apart will be so far that will never merge. So right now, and in the past, that can increase the merger rate, right? If the expansion were less and things were closer, you would expect more mergers and vice versa. So that's something people are trying to measure as they look at those distant galaxies with HST and now with JWST. That's a good question.
Thank you so much. I really enjoyed the night.
Nick has his hand up.
Where'd the hand go? Go ahead, ask your question. Is that Nick?
Yeah.
I didn't see the hand.
The dog.
I don't see it either.
Okay. All right. Well, we can go ahead and move on to the raffle. Did Spencer have to leave? I guess he did. Okay. All right. So I'm going to give everyone just another minute, and then I'm going to close the raffle and get everybody's name, and we'll do that.
Sure. Lots of spectra. I like to see lots of spectra.
Oh, you would.
Yeah, you're used to looking at that stuff.
Dr. Rich, how was Jeopardy?
It was spectacular. I only regret that I didn't win, but it was a once in a lifetime experience.
You look like you got close.
Yeah. Oh yeah. I was already mathing out if I was going to be one of those contestants where if I had run away with it, I wasn't going to bet in Final Jeopardy. I was too chicken, but I didn't even have to think about it. So
awesome.
Okay, cool.
Okay.
If you're on Jeopardy, do you get to join the Screen Actors Guild?
sadly, no.
Sadly, no.
I have two. I did extra work in grad school, so I have 2 Taft-Hartley waivers from working on Lost, but I can't. I ended up on the cutting room floor, so I can't tell you which episode to watch.
It's extremely expensive these days. It's like almost $3,000 after you qualify.
Hey, Jeff, did you do a presentation at a golf course in Palos Verdes the other night?
No, I didn't. I've been to a senior center or a senior group at Palos Verdes a while back, but I haven't been down there in a while.
No, we had a presentation at our monthly meeting the other night. It was somebody that works with the JWST and all that. And unfortunately, I'm a member, but I'm not allowed to go out in public these days. So I missed it. I just wasn't sure if you were the guy that did the presentation.
It wasn't me, but there's a lot going on. So I'm going to watch the Nova special because I'm going to watch all the other stuff that my group hasn't done. There's really a lot happening.
Okay, can everyone see the spreadsheet there?
Yep.
Go ahead.
Okay, I'm going to drop the names in. Okay, first is Jose Aguilar.
Yeah, Jose.
Is Alicia here to tell us what he won?
Yeah. I think Alicia is here.
I'm lurking.
Yeah.
Let's see, where's Jose? I don't see
Okay,
him.
I'm ready for my prize. Sorry, I had the mute on. Couldn't get it off.
I did too. I was like, right?
Oh, here he is,
Where's
right
the
here.
button? You want an Amazon gift card.
All right, thank you.
Okay, you got his email?
Oh, it'll take me a while to copy that one. I have his email still in my account though, so
I'll shoot you the list.
thank you. I think it's written down wrong. It looks like it's written down.
Oh yeah, there's a period in there.
Yeah.
Okay. Ray Bloomhorst.
Oh, hey.
Ray.
Go Ray. What'd he get? What'd he
And
get?
tell lovely Ray what we won.
He won a Celestron Observer's Map of the Moon.
All right. Great,
Okay.
thank you.
Okay, Ray. Elizabeth Purser.
Elizabeth won a red flashlight.
Okay.
All right.
And let's see, where's Elizabeth? There she is. Yeah. Mark Salzman.
Mark,
Hey, cool.
a gift from the LAS store.
Okay, so from the website, go to the
Yep.
store. Okay, cool. Let's see, where's Mark? There he is here. Okay. David Greenwood. David here?
Yep, I'm here. Great, thank you.
David won the Northern Summer Sky and Astronomy Constellation drinking glasses.
Awesome, thank you.
Do we have another?
We have one more.
We have one more. Okay, last one for Ernesto Velasquez. Hey, Ernesto. What's he winning?
Is Ernesto here?
I'm here.
Oh, okay, cool. You won the Celestron Skymaster 15x70 binoculars.
Ah.
Oh, that's good.
Oh,
That's good.
fun. Yeah, that,
That's good.
that got
Thank
him
you.
to smile.
It's been a
I
little
want to make
kid.
sure you were here. I was like, is he here?
Okay, everybody. Well, let's do this. Let's go ahead and officially end the meeting. We can stop the recording, and if there's any more questions for Jeff, if he wants to stay for a little bit, and we can just chat then. So is it Zali? Are you doing the chat? Doing the Zoom?
No, Spencer doing it.
Ah.
I'm
So
gonna
Spencer's
give you a
not
call.
here. I guess it's going to continue to record until we
I'll give you a
all
call.
leave.
Hang on.
Just close your screen share, Daryl.
I will. Thank you.
So Alicia, have you actually used that darn telescope yet?
No, I still fix it. It's be- I've been cleaning it.
It's only